Okay, so hello everyone. Welcome to another episode of the DataBri X webinars. Today is tool session 4, and we will look into tools contributing to DataBri X use cases. So, but as always, first a short overview for DataBri X. So the project focuses to develop a user-friendly toolbox of practical, robust, and scalable bricks, which are processes, technologies, and tools, which can operate on data, implementing a holistic data lifecycle management according to FAIR principles. We also aim to optimize the tool usage, for example, to minimize the energy footprint and integrate with data spaces according to standards like IDSA and Gaia-X. And finally, we aim to reuse existing ontologies, vocabularies, and data models, mainly for semantic interoperability, which are based on semantic web standards. So the DataBri X Toolbox architecture has as its main component the Champlain data governance, where you can design processes using these tools. You can assemble the tools into workflows and specify optimization criteria like the power consumption. And Champlain will automatically pick the most fitting tools for this workflow, and we are able to deploy it and run it automatically, supporting monitoring, orchestration, and the data space connections. In DataBri X, we have 3 use cases, and today we're talking about tools that contribute to these use cases. And these 3 use cases are the operator data space. So this is from Nova, a telecom operator, aiming to optimize their business processes, saving costs and optimizing their business strategies, using a content analysis of communication. The second use case is about the energy data space. So here we are looking into energy communities and simulations for these communities, which rely on a lot of data that has to be consolidated and processed, with the final goal to optimize the energy output in these communities. And the final use case is the legal data space. Here we focus on legal documents as the content, aiming to develop a legal knowledge graph, which is then the basis to analyze these documents and provide services like semantic search and recommendation on top of it. So these are the 3 use cases that we focus on in DataBri X. And today we look into tools contributing to these use cases, starting with semantic search and recommendations from PoolParty Semantic Suite. Then Harry from Athena presenting the KNOwDE and the SimSearch tools. And finally, Tip presenting Maria Esther presenting the SDM-RDFizer tool. And we dive right into it and take a look at PoolParty Semantic Suite. And here we focus on the specific components and the functionality about semantic search and recommendations, which we provide to the use case 3 of DataBri X. So first, a short introduction. Semantic Web Company is the developer and vendor of PoolParty Semantic Suite. It's a whole platform of components, a semantic AI platform, which is based on W3C standards, mainly the semantic web stack. So it's heavily standardized regarding the data models and semantic descriptions. PoolParty has been around quite some time. We started developing it in 2009. We provided as an on-premise solution or a cloud-based solution and have 170 customers worldwide. PoolParty focuses on semantic AI, which is the fusion of different kinds of AI methods, first and foremost graphs, also NLP, machine learning, and nowadays, of course, the large language models, LLMs. So here we see an overview of the PoolParty semantic suite. The core is the semantic middleware, where you're able to develop your knowledge models and work with these knowledge models doing NLP analysis. All the functionality is provided, as PoolParty is a middleware, is provided using web APIs to other applications, which we can see sit on top. This is PoolParty for SharePoint, and also the PoolParty application development framework, which exposes semantic search and recommendation functionalities that we will look into today. So Semantic Web Company has 3 verticals, which are ESG, environmental, social, and governance, intelligent content, and the digital workplace. And today we look into an ESG use case. So this is not a use case that we use in DataBricks, but this is a well-developed use case. So Semantic Web Company already developed an ESG core domain model, which is a fully developed knowledge model that is able to drive this semantic search and recommendations. So here we can see the steps towards building a recommender system. So we start off with building the knowledge model. We start usually off with a taxonomy, a taxonomic structure, which groups the concepts in hierarchical relationships. And this is a very simple basic model. If this is not sufficient, we extend it using ontologies, using classes and properties that can express what we need for a specific use case. So today we already use the developed ESG knowledge model for the recommender case. Then the next step is to apply this knowledge model to your content. So here we focus on natural language. So we have documents of text that we annotate using the concepts from the knowledge model. So we provide semantic annotations using the PoolParty extractor. And to automate that for large amounts of documents, we use our ETL component, Unified Views. Then the third step is to consolidate these documents into a search space. That is then the basis for the recommender, where the recommender runs on using PoolParty Graph Search. The step 4 is then that you create your recommendation engine and you can fine-tune it. So we provide a workbench solution here so that you can test and configure your recommender to the specific needs of your use case. And the final step 5 is then to deploy it and operate the recommender solution using the PoolParty application development framework, ADF, where we provide a user interface that we will see today for search and recommendations, but of course also expose the functionality via web APIs again. So as already mentioned, the starting point is the ESG core knowledge model. This is something we recently developed and provide as a product as well. It's using standardized data formats based on semantic web standards, which is the SKOS, the Simple Knowledge Organization System, modeled using RDF, the underlying data model, and extended using web ontology language R, where we provide classes and properties. So this is basically the foundation of our recommender. It provides a large number of concepts, so it's quite complete regarding the ESG domain. We have 5,000 concepts in this knowledge model. The concepts are identified using terms. These terms are identified then in the documents, 30,000 terms, and it's quite interconnected. So 18,000 relationships connect the concepts with each other, providing semantic information. Here we see how it looks like when we apply this knowledge model to a single document. So here we see a paragraph and the identified concepts highlighted. So we are able to identify these concepts based on the associated labels and also using word forms. So this is our NLP component, the extractor, providing semantic annotations. So how does that look like in more detail? Here we see an example from the ESG domain using the ESG core knowledge model. And on the left side, we see a part of a document. This is a sustainability report. And on the right side, we see the concepts that were identified in the document. So here we see SDGs, Sustainable Development Goals. The first one is about protect labor rights and promote safe working environments. And on the left side, you can see it's identified by several different terms that are all associated with the same concept. So basically consolidating different kinds of textual descriptions of the same concept into one entity of the knowledge model. And on the bottom, we see upgrade all industries and infrastructures for sustainability, which is identified by one label, by ISO 14001, an ISO standard. So we can go a step further and use the knowledge model to draw some conclusions for this document and ask the question which regulations have been addressed. So the SDGs are linked in the knowledge model with other concepts. And here we see that we can identify an Austrian law, the Arbeitnehmerschutzgesetz, that is related to what is found in the document. And at the bottom, the EU EMAS regulation, which is also associated with this document. Going a step further now, we can ask the questions how different documents or parts of the text are related with each other, and take these semantic annotations and interrelate the documents using the knowledge model. And here, for example, we have occupational health and safety and environmental management system. So taking this example again, on the left side, this was identified by ISO 14001. And on the right side, it was identified by two other labels, environmental management program and reduce environmental impact. So both documents talk about an environmental management system and thereby have this semantic relation that we can establish going via the knowledge model. So for DataBri, and we're talking today about use case contributions, this will be provided to the use case 3, the legal data space. Today we are talking about an ESG example. In the legal data space, it will be a bit different. So there we will develop a legal knowledge graph similar to the ESG core knowledge model that we have. And this legal knowledge graph will enable us to analyze, to do a semantic analysis of the legal documents by providing such semantic annotations. And then you can ask questions how different legal documents are interrelated. And for example, for similar court decisions, trying to understand this information in the document in the more broader context. So this is what we will provide to use case 3, the legal data space. This is currently in development. We're busy developing this legal knowledge graph, and we will soon deliver a solution which will be quite similar to this ESG case. But for today, I would like to demonstrate how the recommender works for the ESG domain. And yeah, as recently mentioned, we have two components here, two software components. The first one is the application development framework, which then actually delivers the recommender functionality by a user interface, but also by a web API. So we will take a look at the user interface and see how that works, how we can analyze the ESG-related documents using the knowledge model. And just to mention that this will not be part of the demo today, there's also the workbench that can be used to fine-tune the recommendations. So when you're actively building different kind of recommender systems, this is a valuable tool that can be used for that, and which we will sure use for the legal knowledge graph for use case 3. But for now, let's take a look at the actual demo. So taking a look at the ESG core knowledge model. As you can see on the left side, we have a hierarchy of concepts, a taxonomy with different concepts that have labels and ontological properties. And to connect to the previous example, let's look at the ISO 14000 concept. So we have a concept for that in the taxonomy. All the concepts are identified by URI. So in principle, this is an RDF-based data model. So the simple knowledge organization system builds on top of RDF. So this concept is identified by URI. On the left side, we see the relations that it has with other concepts. We see the broader concepts, we see the narrower concepts, and we see other related concepts. And on the right side, we see the labels associated. This is what we saw in the previous example. These are the labels that identify this concept in the text. So once we identified this concept, we are talking about a semantic entity and not anymore about these separate text labels. This is a basics cost data model, but we also expanded it using the ESG schema, which provides properties and classes from a taxonomy, an ontology, sorry. And what we see here, for example, is three concepts for environmental risk, legal risk, and regulatory risk, which are associated with ISO 14000. Using the property slows down. So here we modeled the knowledge that applying ISO 14000 slows down these three associated risks. So this is something that we can feed into the recommender to determine if documents are related to ISO 14000. This will implicitly mean that they reduce the associated risks. So this is the ESG core knowledge model. And now we take a look at the recommender. So this is the PoolParty ADF, the application development framework. And it implements semantic search and recommendations. The recommendations can also be customized, as previously mentioned. You can fine-tune them using the workbench. Here we have a ready-made system. On the left side, we have to select the right search space here. So this is the search space. There are multiple that we can select from. And on the left side, we see a faceted search, similar to what we saw in the knowledge model. And this actually comes from the knowledge model, so that you can drill down based on the concepts that come from the knowledge model and that are semantically annotated in the documents. But let's go again back to our ISO 14. Let's take the 14001 here and this document. So this document talks about ISO 14000 standard and analyzes the content. We have different kinds of recommendations that we can provide here. And to connect to what we saw in the knowledge model, here is a risk recommender that deduces the risks that are associated with the document based on this link in the knowledge graph. So this is now a quite simple example. So the risks are directly associated with this ISO 14000 concept, but it could also be, we could also model more complex scenarios. So the first different concepts are found in the document, and they could be associated with other concepts via paths in the taxonomy that are more than one property, basically modeling more complex situations. And such a situation is, for example, the opportunities recommender in this case, which shows us that the document talks about an opportunity of energy efficiency, which also comes from the knowledge model, basically saying that if you implement ISO 14000, so you're implementing an environmental management system, and that is also associated furthermore with energy efficiency, being able to optimize in this regard, and thereby providing a more complex recommendation here. So this is semantic search and recommendation, which we will provide for use case 3 in DataBri X. Yes, and with that, this is all from my side, and now I'm happy to hand over to Hare to show us some details for the KNOwDE and SimSearch tool.
Hello from me. I'm Hare Nakos. I work at the Athena Research Center, and I will be presenting two tools to you, SimSearch and KNOwDE. Let me share my screen. So, SimSearch is an open source application that is used for top case similarity search over entities that have multiple attributes and can be found in different and remote or local locations. We'll go into detail about that in a moment. For now, just to let me note that SimSearch is available as a standalone Java application that can be run in a terminal format, and also as a REST web service. SimSearch has been developed in the Athena Research Center, specifically the Information Management Systems Institute. The code for SimSearch is available at the URL at the bottom. So, SimSearch supports combined similarity search against entities that have multiple attributes. These types of the types of attributes that are supported can be categorical, textual, numerical, spatial, and temporal. Queries use different similarity measures per attribute. Specifically, it's a card distance for categorical data, Euclidean for numerical, Manhattan for space, Euclidean for numerical, spatial, Manhattan for spatial, and these are all used for data exploration. Top K, using top K as the road to data exploration to find the top entities among data that have multiple attributes. So, in detail, the attributes supported are set values categorical data, where the similarity is checked against a set of keywords. Textual, where the similarity is checked against the query string and uses possibly uses Levenshtein distance. And numerical, where the values are checked, how close they are together. Spatial, where points are checked, how close together they are. And the k-nearest neighbor search is performed in that case. And temporal, where this is not much different than numerical, where the dates and times are checked regarding how close they are together. So the data sources that can be used by SimSearch can be disparate, and they can again be used together. CSV data can be used where they are loaded and indices are created in memory. Specifically, R trees are created for locations, for points, B trees for anything numerical, and regarding text and categorical data, inverted indices are created. Where inverted index, an inverted index will link each piece of data of textual or categorical kind to the objects that have it. Also, in situ queries are utilized, thus using existing indices. Regarding Postgres containing POSTIS for geodata, these in situ queries are used, are run using the database connector, and also Elasticsearch is supporting, where the query is run using the REST API that Elasticsearch supports. All attributes will produce top K results regarding attributes that are contained in a query, and the appropriate index will be used for each case. And then the results are ranked by an aggregate similarity score that is weighted regarding its attribute separately. The methods used for similarity search are the rank aggregation, top K rank aggregation, which is essentially what we mentioned. Each attribute is ranked separately for among these the entities that have it, and then the ranked lists are combined to give the final top K results using the aggregate score weighing all attributes. The top K pivot search is another approach that can be used. Well, a multimetric index is used that combines all attributes. This index is in memory, and all attributes must be indexed. So this index, so all attributes must be ingested. So this index can be created, and an extended R tree is used for that, because attributes of different kinds must be accommodated. And this approach uses a small number of reference values per attribute, so that distances of a candidate data point is checked against these referent values in order to produce the final top K list. So to go into detail about each API, the mount API call, the mount sources API call will create a new instance of the SimSearch service against one or more data sources. A JSON object is sent containing the data sources to be used and the attributes to use. And the suitable indices will be built for anything that is ingested. An API key will be generated by the SimSearch service, and this will be used to access this instance in future requests. And this is the first operation that must be applied before any query can be submitted. This will be much more evident here using an example, and an example will be used for all API calls described later too. So here we can see that the sources for each piece of data will be CSV files from a specific directory. And the operations that will be used here, starting from top to bottom, is a spatial KNN regarding a position attribute that combines two columns, longitude and latitude, that comes from the sample.csv file. And the key column is article ID. The key column must be present in all files. In this case, actually, the file is the same, but in all file instances, so that all attributes can point to the same entity. Attributes that have the same key column ID. Then we have the categorical top K operation on the same CSV file, and the column of that will be persons. This persons column will take very specific values from a set of values. Then we have the numerical top K for the negative sentiment and the positive sentiment columns. Again, the article ID is the key column. And the last one will be the timestamp column that has a temporal nature. The response contains the API key that will be used in the following API calls. The delete sources, let's go into this very quickly. The delete sources API call will disable attributes from querying. And any attribute that will be part of this call, that was also part of the previous call to establish the attributes that can be queried, will be no longer able to be queried. And this requires the API key that was issued in the previous call. This is the simple way to do this. Then the one is append sources. This API call is very close to the first call that we described, which makes sense. The first call establishes anything that can be queried, and this call establishes extra things that can be queried using the same API key, which is also needed in order to use this API function. And this is exactly the same. As you can see, here we established that the negative sentiment that we previously deleted is reestablished as an attribute that can be queried upon. The catalog API call will return a JSON list of all attributes that can be queried. This requires the API key that was issued in the first call, as we have mentioned a couple of times before. This is the response of the catalog call that presents the kind, numerical, categorical, temporal, spatial, and numerical again, for the respective columns. And we have some metadata as well as part of this query response. And last but definitely not least is the search API call, which will specify the top K similarity search query using a JSON object that defines the description of this search query, and will of course need the API key of the SimSearch instance to run the query against. This is how the search API call looks like. You define the number of K in top K. So here we ask for the top 5. We define an algorithm that is used. This is a very under the hood functionality that will sometimes speed up the process and the response. And the most important part is the query itself, where for starting from top to bottom, we want column persons to have the value of Joe Biden and Donald Trump. And we want the timestamp to have a specific value, and we want the position to have a specific value. And we also define weights, if we want to, where each weights 1 and 0.8 in the first example, each weight will result in a different top K list. So here we ask for 2 lists. We ask for one list where the weight regarding the person's column is 1, and the weight for timestamp is 1, and the weight for position is 1, and this will yield one list. And the second list will have a 0.8 weight for persons, 0.4 for timestamp. We don't care about the timestamp that much, given the lower weight of the column. And regarding position, we have a 0.7 position weight. So in the first, to go just a bit into more detail, the first column will, the first part of the query regarding the column persons will use the Jacquard distance, which will check Joe Biden and Donald Trump, a very specific set of 2 values, and see the intersection of this value among candidate data objects, the intersection over the union, so that anything that is close to this and exactly these 2 values will yield a higher value that will be then weighed with the appropriate weight. So it's the intersection over the union. The timestamp is a more simple distance, and the position is either a Euclidean distance or a Manhattan distance. And part of the result, which, as we can see at the top, uses weights 1 for all attributes, This is, yes, on the right side, we can see part of the results where we see the aggregate score, the rank. Here we can see actually the two first results. And yeah, the values for each attribute. And I'll leave it on for just a few seconds. You can see, especially in the first result, how close we are to the query. For example, Joe Biden and Donald Trump are present in this, and only two other persons are also present. So we have a high score. Regarding the timestamp, we also have a pretty high score. It's just a couple of hours, these two timestamps apart from each other. And the point, well, I cannot calculate it offhand, but these points are pretty close. I mean, taking into account the fact that the score is a bit high. If you see the second result, the timestamp, for instance, the people are more here, so the score of the person's column is lower, and the score of the timestamp is way lower because these two timestamps are more than a few days apart. So this was the presentation of SimSearch, and yeah, if you have any questions, please go ahead.
Thank you very much for presenting SimSearch. So I think we can have the questions then at the end after the presentation of all the tools. So thank you very much for presenting. So the next presentation would then be.
It will be by me again.
About the next presentation would be about the KNOwDE tool, also by Athena and also presented by Harry. So please go ahead, the stage is yours. Thanks.
Thank you very much, Robert. So KNOwDE is a system for data exploration that produces knowledge-based and data-based recommendations, and also provides some graphical data insights to the user. KNOwDE is available as a web application that can be found in the link at the bottom of this slide. And KNOwDE has also been developed by the Information Management Systems Institute in the Athena Research Center. KNOwDE supports queries that consist of keywords and key phrases. This is the first input of KNOwDE. We'll go into screenshots of KNOwDE, presenting a demo of KNOwDE essentially in the end. The user interaction that KNOwDE supports is by allowing the user to select alternative keywords or key phrases and related entities that we will see in the next slide, I think, where they come from. And the relations supported are more general and more specialized terms of what the initial keywords and key phrases were. We focus on the top 5 terms for each keyword or key phrase. And the important part is that these terms should be existing in the data underneath. We will see in detail the data recommendations that KNOwDE produces, and we also see what data graph visualizations are supported. So, KNOwDE has two parts that are connected. The one is the support of knowledge bases. Currently, KNOwDE supports DBpedia and ConceptNet for entities and concepts that are part of an ontology or a taxonomy. And access to these knowledge bases is performed using the API that each one of these knowledge bases provides. The second part of KNOwDE is the data itself. We use the KNOwDE's dataset in KNOwDE's deployment. KNOwDE's in detail is information about projects and results of the projects that are funded by the EU under the Horizon 2020 framework. Specifically, each project has an objective, which is, these are all the fields that KNOwDE makes use of. The project objective, which is the abstract of the project, the short description of the project, which is of the text kind. The project framework program, which is set valued, takes specific values from an array of values. The project members as well is set valued, where each project has multiple members. And the subject areas of each project is set value attribute, and also multiple values can be used. An implementation detail, a very important one, is that the project objective is inverted indexed. This index is used in various parts of KNOwDE. And also a data graph as part of the pre-processing of the dataset is used. Specifically, nodes are used for projects, frameworks, members, and subject areas. And the edges of the data graph comes from the project information for all projects, where, for instance, a project will be linked to the framework, to the members, and to the subject areas that the project has. And all projects, all frameworks, all members, and subject areas are linked to the appropriate nodes. This describes how KNOwDE facilitates data exploration. It does so using producing data recommendations. For this, specifically, we have, for recommendations, we have the top 10 of projects that come as a result of the query. This result is produced using one of these two methods. The one is calculating the frequency of keywords and key phrases within the project abstract, the objective, or using the personalized PageRank algorithm, where the top 10 projects are used, the previous frequency-based top 10 projects are used as seed nodes. And two data graphs are also produced and presented to the user. The first one starts from the top 10 from the previous step and calculates all shortest paths between the nodes of the top 10 list and subgraph. This graph is produced. What this graph denotes is somehow the common neighborhood among these top 10 nodes. I mean, the graph becomes can become big, but could be bigger. It's not that small, it's not that big. The second graph that is produced is the Steiner tree of this top 10. And the Steiner tree presents the shortest connection between the top 10 nodes. This is a really concise approach, concise visualization of how each node from the top 10 is connected to the other nodes from the top 10. Let's see KNOwDE in action. Here is the home page where you can issue a specific query. Here is the query that we have used as an example that will combine the computer science key phrase with the surveillance keyword, assuming that we are interested in projects that combine computer science with surveillance for security purposes. For example, this is the result of the input query of running KNOwDE with this input query, where we can see for each keyword or phrase the top 5 results from the knowledge base, from the knowledge bases used, Wikipedia and ConceptNet. We can see candidate terms that come from these knowledge bases and that the user may use to enhance the query. This is a very important part of the data exploration assistance that KNOwDE provides, where the user can, imagining a cold start where the user has no evidence regarding what the data is available. Here, the user may find terms that come from knowledge bases that have been curated, and the very important thing is that these terms exist in the data underneath. These are not just terms that come from the knowledge base. They exist in the data underneath. Here is the part of the user defining terms to enhance the query. We can see that the user chose computer science, which was also used before, software framework, surveillance, and security. And also the user wanted to specialize from the computer science entity, use a more specialized term, artificial intelligence, that is under computer science in both these ontologies. So this is part of the top 10, which comes after running the query, the enhanced query. Here we can see the top 5. I haven't presented what if we click on one of those entries, then we'll see how the text matches the query. Please excuse me for not presenting a more detailed version of this page. And this is ranked using the personalized page rank. Here we can see the second part of data exploration that KNOwDE assists with. And we can see the graph, specifically the project member and framework nodes that contain the top 10 and also contain the shortest paths between the nodes. I'll leave this on for a while so that you can see projects in red, how they are connected to members, how they, projects connect to members, projects connect to frameworks, which are denoted by the yellow color. And essentially, this is the neighborhood, the common neighborhood of the top 10. This is a standard tree, much more legible visualization, where you can see the top 10 and how they are connected. Using the minimum, the least cost traversal of the graph. This is the other top 10. It's it's different than the previous one, and this is based just on key phrase occurrences. I don't think that I should go in any more detail. This top 10 list is different than the previous one. And this is a different sorted paths subgraph, and this is a different Steiner tree. What KNOwDE does, as we mentioned a couple of times, is to facilitate this drilling down into the data. And these data graphs can be of great use. So, this was supposed to be the cue for questions, but as Robert said, questions will be held at the end.
Thank you, Harry. Thank you very much. So these are SimSearch and KNOwDE, two very important tools that contribute to DataBri's use cases. So thank you very much for the presentations. And we now come to our last presentation for today, which is RDFizer, presented by Maria Esther.
Perfect. Okay, well, many thanks for inviting us to present the RDFizer. And today I will present the RDFizer, but also I will point out other tools that have been developed in my group. So my group is the Scientific Data Management Group at the University, Leibniz University of Hanover, and also at TIB. So can you go to the next one, please? So what is the idea here? We are working in these knowledge-driven ecosystems where we have data sources. The data sources are heterogeneous, so are presented in different formats. And on top of the data sources, there are ontologies that are defining the domain from where these data sources are coming. And there are mappings between the data sources and these ontologies. And also we have the different descriptions of not only the properties that are part of these ontologies or the attributes that are part of these data sources, but also we have operators. And as you will see later, in one of these operators is, for example, the operator of entity linking. And the operator of entity linking is the one that allows for extracting from textual material that can be a particular type of data source, for example, a PDF, into entities that at the end are going to be part of the knowledge graph. So if you can click the next, please. Okay, but when we are seeing here, what is very important is that we provide services for creating this knowledge graph, for example, but also to enable the access of this data and the discovery of knowledge on top of these data structures that we call knowledge graph. So please, the next one. So these knowledge-driven ecosystems are also connected. So that means that we have developed these knowledge driven ecosystems, when, for example, we have one data ecosystem that corresponds to all the data that belongs to a particular partner, and then we have each of these data ecosystems for different partners, and we connect everything. And is the knowledge graph the one that supports these connections? So we can go to the next. And here, all of us know what we are referring to a knowledge graph. So a knowledge graph is a very simple data structure that enables the representation of knowledge and data by using factual statements, but using these data graph models. So please next. And what is important is that we are able to represent as the factual statements, data, entities, relationships, metadata, and everything lived together in order to empower the inference process on top of this knowledge graph. So the next one, and here what we are, something very, very important in the language that in the SDM-RDFizer is that we have a concept of data integration systems. And the concept of data integration system, together with what we call from the beginning the knowledge-driven ecosystems, is basically what allow us to define declaratively this knowledge graph, and also what they allow us to give the input to the SDM-RDFizer. So basically, we assume that we have an ontology and we have the data sources, which can be in different formats, as I was saying before, and we have the mappings. And these mappings state the correspondences between the ontology that is defined, well, using any methodology of ontology definition, and the sources that are provided by, in this case, for example, the partner. So please go next. And when we are talking about the process that these tools that are part of the my group or have been developed in the context of my group, but what we are just having is ontologies, we have data sources, and we have the mappings. And on one hand, we have the SDM-RDFizer, that is the one that executes the mappings on the data sources in order to populate the ontology, but also we have the possibility to validate the quality of the data that have been integrated in this knowledge graph. And also we are able to traverse, to write queries, and these queries are not only over one knowledge graph, but also over several knowledge graphs, in the way that this integration of the knowledge graph can be, we can interoperate with this query engine that in this case is called the Trusty. So please go next. And when we are talking about, so next as well, so when we are talking about mapping languages, so we are focusing in declarative mapping languages. In particular, please click, we are, our focus is next. Our focus is in R2RML or also to RML, even though the techniques that we have developed could have worked for other approaches. But our aim and what I'm presenting today has the focus on what we call RDF triple-centric mapping languages, and in particular with R2RML or RML. So please go next. Just to recap, what is RML? RML is R2RML is a mapping language that is able to specify mapping rules for relational databases into RDF. And what is interesting from this mapping language is that, first of all, it's a recommendation language for specifying these mappings. And second, that this is expressed in RDF, which make the mappings another part of the metadata that can be included as part of the knowledge graph. And this is something that also we are able to manage. So please go next. And RML, on the other hand, instead of just considering, well, having the properties that we define for R2RML, we have a possibility to also receive as input data sets that are in XML, JSON, CSV, and relational tables, for example. And the output always is in RDF. So that means that they have defined a new data language or a new mapping language that is able to receive a different type of data sources and is able to map using the subject map and the predicate object map into instances of a knowledge graph by having by using what are called triple maps. So go next. So, and something is very, very important to highlight is that there are several engines that are able to work or generate knowledge graph based on these mapping languages. So, for example, RML, or as today I'm going to present the RDFizer, happen to be that when, and this is a paper that we presented some years ago, so something that is a fact is that there is no the best engine. Happen to be that under different conditions, the different engines are performing differently. So there are many challenges that need to be addressed in order to guarantee that these engines are able to scale up to real scenarios. So please go next and next, so twice, okay? So that means that the engines are actually impacted by the complexity of this data integration system. So just to give you an example, please click next. So what we have here is that every year in the context of the extended Semantic Web Conference, there is a challenge in the context of the workshop of knowledge graph construction. And the challenge is to evaluate, to assess the different engines that exist for generating or creating this knowledge graph. And in 2023, for example, the RDFizer was the one that won the task-specific award. But when we were comparing with different tasks, see that there is not an engine that at that time was overcoming the other engine. So go next. And this year, when we had the same context or the same challenge, what happened is that, okay, the RDFizer is the one that was covering all the new definition of the RML, but there are others that were winning in performance, but were not able to actually compete with the or cover all the specification of RML. And that means that they were in this challenge where was, if you see here, a long list of test cases where the idea was to see how these test cases could have been achieved by the different engines. As you see here, in order the RDFizer to win this award, we had to implement all these test cases or pass all these test cases in order to guarantee. But still, the problem that we were seeing before, that there is no the best engine, exists. So please go next. So then what happened with the SDM-RDFizer? Well, the SDM-RDFizer is actually an engine that we can say is competing in all these challenges and is winning this award. So go next. So the key point behind the SDM-RDFizer is that we are implementing data management techniques. And these data management techniques are the ones that are able to transform RML triples and data sources on different formats into knowledge graph. And with that, we have two stages where the first stage, we are planning the execution of these triple maps in the same way that we are planning when we are, for example, planning the execution of a query that is evaluated over a knowledge graph, for example. So we apply and we see this as an optimization problem. And on the other hand, we have physical operators and physical structures that are the ones that enable the execution of these plans that are selected in the first step in an efficient way. So if we see this architecture that I'm presenting here, is an abstract representation of what the SDM-RDFizer does, is that in a first step, is considering the mappings, is grouping these triple maps in the way that the triple maps that are over the same data sources or that share certain characteristics are grouped together. And then there is a planner that is planning how this should be executed in the way that the execution time and the memory consumption is reduced. On the other hand, as we will see here, when we are thinking in terms of the physical execution of these plans of mappings, what we have is first physical structures, and the physical structures are the ones that guarantee that the amount of memory that is required to execute these triple maps is minimized. And on the other hand, these physical structures are also devised in a way that the execution time is reduced. So we are aiming to the minimization of two problems. One is consuming memory, and on the other hand, is reducing execution time. So if we go next, please, we will see that when we go inside and we see the physical operators, what is very, very important is that we have physical data structures. And these physical data structures are the ones that are keeping everything that is generated in the way that duplicated triples are not generated twice. So that means that each time that a tuple is or a triple is output and inserted in the knowledge graph, we are sure that these output triples are not duplicated. So in order to do that, so the RDFizer maintains two data structures. One is what is called predicate tuple table. That is the one that per predicate that is generated stores the triples generated so far. And the predicate join table is the one that keeps what has been generated when there are joins between the mappings. And in order to manipulate what is stored in these structures, we have physical operators. And the physical operators, one is the simple object map, the other one is the object reference map, and the other one is the object join map. So can you please go next? So just to give you an idea, so what happens when we have a predicate tuple table, what happens is that it's storing per predicate that we are generating in these knowledge graphs, is storing a key that corresponds to the subject and the object of what are the triples that are generated. And this is encoded in the way that the space is also reduced. So for giving you an example, so suppose that we have these two tuples that were generated for the predicate gene label, and what happened is that in this index structure, what we have is the encoding of the subject and the predicate, the subject and the object of these triples that were generated. So please go next. And then what happened when we have a join? What we are representing is what is called an index has table, where in a join, always there is the outer join or the outer table and the inner table. In this case are not tables necessarily, because remember that we are talking about a data mapping language that receives many different type of data sources. But what is important here is we have the abstraction that we have the outer argument and the inner argument. And this is what we call the source one and the source two. And what happened is that this index structure is keeping an index for each of the tuples that are used or have been joined in the process of execution of these joins, in order to avoid that when new tuples or triples are generated, duplicates are also generated. So please go next, and then you will see what is the meaning of that. So imagine I have these two triple maps, triple map 2 and triple map 3, and basically triple map 2 is having a join, with the triples map 3. And basically what we have initially, we have this data in the data sources. So please go next. And what we have is actually create an index. So create an index based on what we have in the source tool that is linked or join, make them the join, the match with what we have in source one, but we have the value of that index corresponds to each of the values in S2 that correspond to that join. So for example, in this case, you could see that for the ID sample 2193,351, we have these two values. And for the 2196,270, we have only one. So please go next. And then we have a dictionary table where basically for every resource that we receive, that we create an index. And this index is actually encoded in the way that the space is reduced. So this is what is helping actually to avoid repeating and storing very large strings representing resources. And what we have is that we have a key RDF resource, and this is represented as a value identification number in base 36. So that means that with that, we are reducing considerably the memory that we require in order to keep all these data structures. So please go next. So, and this as an example that you could see, instead of having these particular strings that can be very long and could require having all these, using all this space, we are reducing everything to these dictionary and hash tables. So go next. But how we use that? Click 3 times. How we are using that? What we are using is that we have the physical operators, and the physical operators are the ones that allow us in order to execute this mapping. So click. So basically what we have is different type of mapping assertions or these triple maps. And what happens is that we have different physical operators. So for example, the projection, the selection, the natural join, and the self join. Next, go next. We know all that evaluating this is very expensive. However, thanks to the implementations that we have for these data structures, go next, and for the algorithms that we are implementing to have these physical operators, for example, the simple object map, we are able to receive a particular data set. We execute, for example, in this case, the data set S, and we have the triple map that is having the subject and the object, and by using this operator, click next, we are able to generate new triples and avoid that the triples that are repeated or duplicated are generated more than once. Next, please. And then in the same way we are doing for generating what we call object reference map, and click next. And the object reference map are the ones that when we have triple maps that are defined over the same data source, the engine is able to efficiently execute this join in the way that is keeping all what is necessary in order to generate the triple that is not duplicated. So saying that is receiving again a triple map, is verifying that the join between these two triple maps is over the same data source and is avoiding the duplicate generation. So go next, please. So, and this is encoding. So the encoding is the function that actually is transforming that in this encoded value that is representing very few memories. So go next. And for the join, go next. I think it's fast, it's better that you click. So what happened is that now we have joined between different data sources, and actually the operator is able to create first the structure that I was describing before, the hash, the index hash, but is able also to verify that a particular tuple that is intended to be generated doesn't exist already in this hash, in the index hash, and in case it's not, is generated, the data structure is updated and is output into the knowledge graph. Otherwise, it's basically doing nothing. So it's not duplicating the tuple and it's not adding anything duplicated to the knowledge graph. So please go next. So how we have, go next. Okay, so how we are guaranteeing that these operators and all what we are implementing is actually efficient. So, and how we compare this with the state of the art. So as you see, all our work is coming from a research team. So all what we are implementing has to be a contribution to the research area. So in this case, all the papers you see in the slides are cited. And in this case, what we have done is to use state-of-the-art engines, as for example, RML Mapper, MoreKGC, the SDM-RDFizer, and the Rocket RML. And not only we use the engines that are in the state-of-the-art, but also we use the standard benchmarks for assessing the performance of this engine. So these are the standard benchmarks, is also the state-of-the-art. And what happened is that these benchmarks are capable of considering many different types of complexities that may exist in a data integration system. Not only the size of the data sources, but also the shape of the triple maps, the connectivity between the data sources, the selectivity of the data sets when they are joined via the triple map. So all this is part of this configuration. So into the case that we even have very, very complex triple maps that are connected via joins. And these joins are, as all of us, one of the most challenging joins to be executed are what they call multiple. They have multiple sources, but also that we have stars that are connecting all these joins with a particular type of data source. So if we go next, you will see that first of all, see that until now I have shown several features that the SDM-RDFizer presents. And over the time, we have developed, say, the data structures, the operators, and so on. And something that is important also to assess if actually these features that we have implemented are features that are reducing what we wanted to reduce, that is execution time and memory. And as we could see in this figure, when we are assessing or evaluating the SDM-RDFizer over this benchmark, that is the Madrid benchmark, we can see that we are able to reduce execution time, but also memory. Go next. But it's not only that when we compare with respect to us, when we compare with respect to the state of the art, that are SDM-RDFizer, MoreKGC, and RML Mapper, the SDM-RDFizer is, in this case, in terms of execution time, competitive with MoreKGC. But when we are thinking in terms of memory, the memory is actually less. And less because we are able to encode. And it's worthy to mention that this benchmark, the GTTFS Madrid benchmark, is a benchmark that more or less was defined in order to assess the features of the MoreKGC engine. So we go to the next one, please. So in this case, we see that this is a benchmark that was defined independently of the engines. And we start having different type of cases, no? We have A, B, C, until H, where we have different type of, the size is changing, but also the duplicated rate. And when the duplicated rate is where we can see that actually all these data structures that we are defining are data structures that at the end are very beneficial when there are data sources that are overlapping or when we have duplicated values in our knowledge graph. So if you click, you will see that actually, please, okay, there are cases when the cases are complex. That means that when we have these stars in the triple maps, and second, when we have a high percentage, when we have data sets that are relatively big, but also that we have duplicates, that we can see that the SDM-RDFizer is outperforming considerably more KGC. Of course, in cases where in configurations where we don't have very large data sets or the mappings are not so complex, it's competitive. But when we do have these complex scenarios where memory can be consumed because the data sets are big, or because the triple maps are complex, this is showing, these results are showing that definitely the techniques that we have implemented in the SDM-RDFizer are the ones that show a better performance or exhibit better performance. So please click twice. Okay, so now what happened is that we are not only having these physical operators, but we are able to plan the execution of these triple maps. And what we have done is seen this as an optimization problem, where actually what we are aiming is to reduce the utility function value. For example, the value of memory that is consumed, or the execution time. So please click twice. All of us know that this problem is a very complex problem. And what we did is to define the physical or this planner that is able to be executed not only over the SDM-RDFizer, but also that is able to optimize the triple maps and give plans to the existing engines in order to speed up also the execution time of existing engines and reduce the memory consumption. Just to give you an idea, without going into much detail, we are able first to fragment the data sources in order to guarantee that we have normalized data sources as when we study relational databases, then that we are able to have the physical plans that are the ones that minimize the execution time and the number of duplicates that are generated. And basically, at the end, we are able to execute, in the case of the SDM-RDFizer, using the physical operators and the physical structures, but in the case of the other engines, we are able to pass this to the other engines and also execute the physical plan. So please go next. And you will see, next please. Okay, that we have also evaluated in the state-of-the-art benchmarks. Go next. And what we can observe, you probably will have go next and see that we are comparing the SDM-RDFizer, the RML mapper, and the more KGC. And what we can observe is that by using, well, again, when the scenario is not complex, probably the savings with tools as the SDM-RDFizer and more KGC that are more tuned for complex scenarios are not so big. For example, with RML Mapper, that actually requires all this optimization process in order to enhance the execution of it. So please click, I think you can click 3 times. Yeah, next please. And you will see that actually there is not, well, in simple scenarios, can be costly. For example, for more KGC, go next. But when things start to be complex, see that is required. So that means that these planning techniques, as usual in any scenario when we are planning to optimize a query or the execution of a particular plan, is costly. It's costly to find the plan. It's not necessarily having a plan for a simple scenario is the best. But in this case, what we are clearly seeing that when we have complex scenarios where we have large amount of memory or large data sets and complex triple maps, this is also a way to go. So please go next. And this is similarly showing the same, right? Now we have, and we are trying to see when we have duplicates and see that, again, the savings are similar to what we presented before. So we can go next. And now I'm going to show you next an example that we had in a European project. So now that you are discussing about European projects, and it was in the energy sector. And in there, we wanted to create a big knowledge graph, but we were trying to understand what was the impact of generating all this knowledge graph in RDF first, and how expensive was for all these engines generate this knowledge graph, how much memory they needed in order to generate the knowledge graph, and how costly was this in terms of also execution time. So you can click, and you will see that we started with the different engines that are available, and we were checking, okay, what happened? We measure elapsed time, we measure memory consumption, and we saw that we have the different output size. But what is the first observation that we had? First of all, see that we started with relatively small data sets, but the engines were requiring a lot of memory in order to execute the pipeline, particularly in engines as more KGC. Why? Because they are using particular type of data structures. So that means that, go next, that we had to use actually something that, well, was impacting scalability. So how can, for a data set that was so small, we were requiring how much memory? So was something that if we were thinking to use data, big data, this was not the way to go. So go next. And here what we did is that now, okay, so next again, what we did is was to optimize. So now if we optimize with the planner, we see that we are not only reducing execution time, but also the memory that is required. Still is considerably the amount of memory that is necessary, but why? Because remember that the original data sets are semantified and annotated with these ontologies, and these annotations that correspond to the metadata are the ones that are consuming all this memory that we are observing. Actually, when we are comparing the output size, so it's important to see the output size. When we are starting without planning, we will see that the output size is smaller than the memory that is consumed. But after we are able to optimize, we will see that actually we are consuming less memory than the size that is the size of the knowledge graph that is generated, which actually was something that was acceptable. Why? Because first of all, if we were saying that we are semantically annotating these data sets and creating a knowledge graph that includes the data plus the metadata, what we wanted to have is that as maximum we will consume the same size in memory when we were creating the knowledge graph. And what we see here is that if you can observe, it's not that it's just to emphasize that, but the SDM-RDFizer sends to these data structures that we were defining and presenting before is the one that is able to produce or consume less memory. So go next. Yeah, click, and we will go next. Okay, so before, please. Okay, so the SDM-RDFizer is publicly available. So as you see, we have it in our GitHub, we have it in KNOwDE, we have it in using this license. We have a Docker image that anyone can download. We have documentation, and that Enrique is going to show you as well. We have videos. We have used that in different projects, and everything is also publicly available. So go next. But it's not only that we have the SDM-RDFizer. As I was starting from the beginning, what we have is a portfolio of tools that are supporting all this pipeline of knowledge graph creation. So we start with data integration. As I said before, we have entity recognition and linker that is able to link recognized entities to the Wikipedia and Wikidata, and this is Falcon, and is very well known and used in the community. We have the Trusty, which is a federated query engine that is able to interoperate across different knowledge graphs. We have the Trusty that is also available. We have the Trap Shackle that is an engine that is able to execute shackle constraints over knowledge graph and also over data integration system. So that means that not necessarily the knowledge graph has to be created in order to execute the shackle constraints. And we have InterpretMe that also is a framework that is able to explain the decisions made by the machine learning models when data is collected either from knowledge graph or from data sources that are planned in different formats. Okay, so all these tools are publicly available, and anyone can access our repository and can even see videos on how we are putting everything together. So next, I think, is the picture of my group. Oh, well, this is for the RDFizer. These are the 2 awards that have been actually we have received. So any question, you can even go to our website. You can contact Enrique. You can contact me, and everything related to the SDM-RDFizer. Also, you can check it in Google Scholar, and then the picture of my group. So you couldn't imagine that it could have been done. Go next, please, without a big group of people that belong to my group. And these are all the people who are participating in this project. So, well, many thanks. And I'm ready for questions if you want, but Enrique has a demo that if you are interested, he can show it.
Okay, hello. So let me get more.
Yeah, probably you can, let's see if you can share the screen, Enrique.
Okay, by any chance, can you see my camera? Hopefully with that is.
No, yeah. We still cannot see it. Yeah. No. So it seems we have to skip that for today.
Yeah, well, I'll try to give a basic explanation what I was going to show. So I'll do this relatively quickly so not to waste any more time. The SDM-RDFizer, as Esther mentioned, is a knowledge graph creation engine. We have over time developed multiple different ways to how to execute it, but every single method has the same input. It receives a configuration file which allows the user kind of to customize how they want the execution to work. So if you have multiple files there and you want only one output, it allows you to give you only one output. If it's a database, it allows you to input information, different things like that. And the most important thing is that the RML mapping needs to be correct. The reason behind this is that the RDFizer receives all its information of what the sort of data source is being transformed, what sort of attribute the class has, everything that is being that is received through the RML mapping, which is the input of the RDFizer. Of course, as I mentioned, there's different methods. You have the standard execution where you just take the script and execute the script directly. We have a Python library in PyPy, which you can actually download, and you can either incorporate it to your own script, which some of our work, including an application called InterpretMe, does. It also we have a Docker image. The Docker image is a good way if you want to like serialize different tools to kind of execute them in parallel. So all of this is publicly available on GitHub. Feel free to take a look around. And as Esther mentioned, are my emails at the end of the presentation. So if you have any questions, you can. Thank you very much. Quite unfortunate that everything. Bye-bye.
Thank you very much for this very quick summary. Yeah, I'm very sorry for the technical problems, but I think we are very close to the end of the session, of the webinar. I think it's time to have some questions, if there are some. For all the tools, as promised, we can take some questions. Okay, I would have a question for RDFizer actually. I'm interested in the technical frameworks that you use. So, I mean, this is a very challenging task to optimize that regarding memory and performance. And by the way, congratulations for winning these awards. It's a great achievement, I think. You looked into the very details of these performance optimizations. Did you implement all that yourself, or are you building on existing frameworks like open source frameworks and such?
That's a very interesting question. As Martha showed, different engines have different memory consumptions, and the engine that has a similar construction to ours is MorphKGC. We noticed that MorphKGC is an engine that is I know I'm starting talking about a different engine, but there's a reason there's a logic behind my madness. It's an engine that is completely built on pandas. Pandas is quite good because it allows them to work in parallel, but it consumes a great deal of memory, a great deal of memory. When I noticed when I started working on a particular project, I noticed that I was consuming more memory than I should. It was weird because I could have a data source that was, for example, 1 megabyte, and I was consuming over 500. And I was like, and I did not, I have to move this now. I did not understand what was going on. What happened was I was using pandas as well, and unfortunately, pandas, which is quite good, helps speed things a great deal, but it consumes a great deal of memory. So after I noticed that, I started to use the basic libraries that exist within Python for the overall going through the data sources, but everything else I tried to program and optimize on my own. That's why when we have this data structure duplicate removal, we said, oh, good. This is quite good because when it finishes, everything going to be handy. But if you're generating a knowledge graph, well, you're going to have the virtual copy of the knowledge graph in memory. So the best way to deal with this is one, reach a point and realize that some of the things that are being stored need to be purged. And two, when I have to store something, something has to be as small as possible. That's why we're using these different techniques. All of this I have been implementing over time. I don't want to use trial and error, but things I've been testing out, and over all of this has been from works I have seen, experiences I have had, tests I have run, and everything has coalesced to what I have now. So yes, to put it short, yes, most of it I have tried to implement myself, so I don't have the excuse to say it's not my fault. It's the thing that I'm using. So yeah.
Okay, thank you very much. Thank you.
No problem.
Any other questions? Okay, I have another question for Harry. I'm interested. You presented KNOwDE, and you explained that this is based on a sort of data model for EU projects, right? So this is running on top of a existing data model. So what would be the steps to use it for a different domain, another data model, or is it possible to apply that to a different knowledge domain, or using different knowledge models?
Okay. So you mentioned the data model, the data underneath, and the knowledge model. So these are the two two parts that together form KNOwDE. And regarding, let's start from the, maybe it's the easier one. The knowledge model uses APIs from currently for each of the two knowledge bases, DBpedia and ConceptNet. Another a way to use another knowledge base would be to use an API that some knowledge base would provide, or even use a local deployment of something using maybe a graph database or even a relational database, and extend it using a custom taxonomy or ontology. So the part of the data model is has just maybe a couple of prerequisites, and this should pass through a pre-processing step. The prerequisites are that there is a text part for the data, for the entities, for the data objects, and this text is what the knowledge base would work on. Actually, this text should be pre-processed to provide an inverted index, and this is where the knowledge base then would, where the querying would happen, and the knowledge bases would be used also to enhance the query.
Mm-hmm.
And there is another, and the final part of this integration, which would be regarding the data graph, and that these data objects should be linked one way or another, like in the Cordis dataset that we used. A project would be linked to other projects using the framework, the members. I mean, this is all about providing and assisting with the data exploration using these data graphs. I mean, if data graphs are of such importance.
Mm-hmm. Mm-hmm. Okay, thank you very much.
Thank you.
So I think for today we are at the end of the webinar. So thank you very much for joining. Just as a final message from my side, I would like to mention that we will have, of course, the next episode of this series where we continue to talk about the tools for use cases. However, we don't yet know the specific date for that, but we will announce that very soon. So I would be happy if you join again the next time. And for today, thank you very much again for joining, and see you.